Hi, everyone. Welcome to an advanced algorithms student lecture on a topic that we found interesting, which was the couch surfing dilemma and node visitation problem. This is brought to you by Nick Squared. So I'm Nick.
And I'm Nick.
And we're going to get into some of this fun node visitation dilemmas.
Okay, so to introduce the couch surfing problem, let's start with an example. So, our good friend Emily got a job in the Bay. Yay! Unfortunately, the job doesn't start yet. It starts in 3 weeks, and she doesn't exactly have a place to stay. And with Bay Area house prices and rent, she would rather not get a hotel or an Airbnb, and she would rather couch surf with her friends in the area. So lucky for her, she has plenty of friends and less good friends in the area. She would love to stay with people like Prava or Vicky, and she would prefer not to stay with frat bros, dogs, sliced bread, or the coronavirus. So Emily's problem is trying to find out whose couch to crash on and when. So this is subject to several constraints. First, Emily can only move so far in a day. She does not have a car, so it's kind of limited to how far she can walk, and she would prefer not to sleep on the streets. Emily would like to maximize the amount of time that she spends with her good friends. And then also, the longer she stays with a friend, you kind of get sick of each other. So the more time nights she spends with one of her friends, the less happiness that will be derived from spending time with that friend. So in order to approach this problem, a kind of key first step is to abstract it. And how we've done that is we've taken kind of this array of friends here, and we've converted them into nodes, where the weight of each node represents how good a friend that person is to Emily. Next, what we can do is we can connect these nodes based on their physical distance to each other. So for any node, it will be connected to other nodes that are within a day's walking distance. So with these two things, we now have an undirected and node-weighted graph that accurately kind of represents this problem. One kind of interesting thing with this graph is what we can keep track of, which is the connectivity, meaning the maximum distance it takes to get from any node to any node in the graph. For example, if you look at this graph, the connectivity is 3 because you can get from any node to any other node in the graph by making a maximum of 3 jumps. So, kind of relating it back to the original problem, we would like to maximize the weights of nodes in a path on this graph from a given start. In this case, the start is that 0 in the center. And what we would like to do is find the maximum path of size x, where x is the number of nights that Emily needs to survive. You can visit the same node more than once, just like you can stay at a friend's house more than once, and you can visit the same node sequentially, aka stay there more than one night. So to begin to find an algorithm to solve this problem, what we want to do is we want to come up with some kind of upper bound, right? Some kind of ideal solution, and to get an idea of how good that solution is going to be. So the absolute ideal solution for this problem is at any point in time, taking the weight of the maximum weight in the entire graph and then decrementing that weight as we normally would, right? So if we saw this graph here with nodes A, B, and C, what we would do is first we would find the maximum weight, which is C, and we would append that to our list and then decrement it. Next, what we would want to do is we would find the maximum weight. In this case, it could be A or C, but let's stick with the same one, C, and let's decrement it again. So now we have a list of C15 and C14. Then we see that A is the top weight, and we can decrement that. And then we can continue on in that same fashion, constantly decrementing the top weight, until we have this final list, C15, C14, A14, A13, and C13. So we can generate this list that provides an absolute upper bound to what a solution to this problem would look like. No solution, possible real solution would be better than this. So we can then use this upper bound to get an algorithm that we know is within some factor of what is the optimal solution. So in this one, what we do is we run through these values in the upper bound and navigate from point to point. So in this case, we start, let's say we start on node C, and we see that C is the optimal. And we say, great, let's add that to our list. Let's stay there again. We see in our goal that C's there again, and we say, great, we can stay there again. But then we see the next one is A14, and A14 is 2 away. So now we use a standard path planning algorithm in order to find the shortest distance to A, and we navigate to that. So what that would look like is we would first add B to our list of nodes where we stay, and then add A. We would then stay at A again, just like our goal dictates. And then we would see that once again, C is better, and we would navigate back right in the same way. So what we can see is that we can navigate between these nodes, and our list will look like the ideal list. However, it would have these kind of nodes in between, which are not as valuable. So our claim is that this algorithm will generate something that is within a factor as good as the optimal. And the reason for that is, you notice we generate a list that contains all of the things in our maximum, right? Well, we only need to say there X days, so we take the first X from that list. And if we consider a graph with this connectivity D, we know that the length or the distance between any two nodes in our goal list, in our kind of the list our algorithm produces, will be at most D. So at least 1 over D of those of the goal nodes will be in our list, in our algorithm generated list of nodes to visit. And because these nodes will be the maximum 1 over D, D kind of percentage of the goal list, it will be at least 1 over D as good as the ideal. As far as runtime goes for this, if we define these variables, N for the number of nodes, E for the number of edges, X for the number of days, and D again for the max distance between nodes, generating this first list using a max heap is a N plus X log N operation. Then finding the optimal path for each node in the list is going to be using a breadth first search, because this is unweighted, we can use breadth first search, would be O of X times N plus E, which is a valid, which is larger than the other term, and meaning our total runtime is X of N plus E.
So we just learned about our algorithm. However, not all algorithms work perfectly in all scenarios, and we want to find out where our algorithm breaks. We really want to find out the edge cases so that we can look at them and see where we might not want to use our algorithm. The first edge case is in a sparse graph. A very sparse graph means a high connectivity and a very high distance, average distance between two nodes. What this means is that we have a relatively large D in our equation, and so our guaranteed answer of 1 over D would be small in comparison to the optimal solution. In this case, you can look to see our graph currently shown, where we have nodes A through E connected in a straight line. We start at node B, and we look around and we see that although A is a very good node to stay at, E is technically better because it is the global optimum right now. So day 1 we travel to C, day 2 we travel to D, and day 3 we travel to E, and we finally reach this value we're looking for. What this means though is that our solution can be okay, but not as good as prioritizing nearer nodes and making sure we hit the highest happiness in the nearer nodes. And this just kind of shows a little bit of a shortcoming of our algorithm. The second shortcoming is actually related to the number of days. If there's a relatively small number of days, especially in a sparse graph, Emily might not even be able to reach the first max node, much less subsequent ones. And this leads to a much worse solution despite the nominal guarantee of a 1 over d solution. In this case, we're going to use the same graph as before. With 2 nights, we are able to travel to C and then D, but are unable to reach E. Therefore, it would actually have been better if Emily had just gone and stayed at A for 2 nights instead of trying to get to E. And this just kind of shows one of the places where our algorithm works a little bit poorly in comparison to other potential algorithms. Now, in the third situation, this just highlights a case where our algorithm doesn't perform any better. In edge case 3, all nodes have about the same happiness. And what this means is that we don't really have any peaks to go to. Our algorithm will basically take an arbitrary path and or random walk, depending on your perspective, and it doesn't do any better than other algorithms. It gets trapped by the dead ends that you can see on the left side of the graph shown, and it doesn't avoid them, such as more complicated algorithms may be able to. And it doesn't have like a massive speed increase or anything. And so it kind of doesn't have any major pros to use in this type of graph. And those are just 3 of the edge cases that we were looking at for a solution. However, as part of this, we need to compare these edge cases to other solutions. So what are these other solutions that we're looking at? Before going into them, we would like to note that all solutions are set up, so to speak, in the same way as ours. So the graph of all possible places to visit are just limited by the distance, and the nodes are weighted by similarity of interest in just the exact same way. So we are only looking at the solving of the graph, not the creation of the graph for our algorithmic comparisons. The first comparison we're looking at is the full search. In this, it's just basically a brute force solution where you recursively go through every possible solution. And this sounds great, right? Because if you go through every solution, you can find the optimal solution every single time. And it has a really good space complexity, O of x, just based on the number of days. However, the time complexity really is the biggest issue with it, where every day you have to make A comparisons, where A is the average number of neighbors a node has. And you have to do this X times. And that really compounds itself as for each layer of recursion, you have to perform A comparisons, and this leads to an A to the power of X, or an exponential runtime, which is always suboptimal. Because of that, this is super time intensive and really is infeasible for any non-trivial network size. On the contrary, the greedy search is a lot faster. What a greedy search does is that looks at the current neighborhood that it can see, and it just goes to the happiest node that it can see between the current node and all neighbors. And it just repeats it for X days, and that's your solution. Same space complexity because we have to save the solution. But time complexity is a lot better because we do A comparisons only X times. So we have a time complexity of X times A. And the pros about this is that it is relatively easy to implement, and it has a really fast runtime. The big issue with the greedy search is that there is no guarantee of the quality of the solution. In our solution, we have a 1 over d quality. In the brute force solution, we have guaranteed maximal solution. But greedy search doesn't have this, which is why in some cases, if you need some standard of solution, you cannot use a greedy search. So we went through all of this and we gathered a whole bunch of insights that we'd like to share out about what we learned about the algorithm and other algorithms when solving this problem. So our first insight is actually that our solution is a good first pass algorithm, but it isn't optimized further. There are a lot of ways we could go about this, with 2 leading examples being you visit the nodes that have the highest average for all days in the optimal solution, and then you stay there for the duration that they would be stayed in the optimal. Or another way to optimize is that if you have 2 nodes of the exact same value, you always visit the nearer node instead of going to the farther node or having a random choice. And there's just other small optimizations such as this that can make our solution much better when implemented. The second insight is that our quality of solution is directly correlated to the density and connectivity of the graph. The denser and the more edges that on average a node has, the better our solution will be, because it's always bounded by 1 over d. Finally, there are a lot of other considerations that should be taken into account when determining people's happinesses. And what we were doing was an abstraction, and if we were to actually implement this, we'd take a lot more into account into the creation of the graph than we actually did for algorithmic purposes and for our examples.
Right, so what should Emily do? Well, if Emily, as a general strategy, at any point looks among all her friends and finds one where staying with her would make her the happiest, using our solution, she should just take the shortest path to get to that person and stay with that person for as long as it makes her the happiest. And when there's another friend that makes her happier, make her way towards that person. This may hurt some feelings, but using this, it is guaranteed that she will be within a specified factor within of the ideal path that she could take. So we argue that this would be a very effective solution to solve Emily's problem. So overall, thanks so much for listening to us.
Thanks so much and take care.